All right. Well, first of all, thank you everybody for showing up today, especially at 9 o'clock on a Saturday morning. I appreciate it. What I want to talk to you.
Could you give us a forward back?
What I want to talk about today is a new concept I call dynamic binary visualization, and I think this is a pretty important and interesting topic because I really view this as the future of reverse engineering, which I think is a pretty bold statement, but I'll let you be the judge of whether or not that's accurate at the end of the presentation. So before we get into things, I've got to go through the obligatory bio slides, and these are kind of dry and boring, so I'll try to speed through this. Basically, my name is...
A little closer, they can't hear you.
My name is Domas. I'm an embedded systems engineer in the Cyber Innovation Unit in the National Security Division of the Battelle Memorial Institute. Now, a lot of people haven't heard of Battelle, but we are the world's largest nonprofit R&D organization, and we manage some of the leading national laboratories around the world. So I'm not here to be a show for my company, but we do a lot of cool work. Hopefully some of that you'll see today. So diving right into things, what I want to talk to you about is reverse engineering, and specifically our view of reverse engineering as a type of information analysis. And in other words, we get a big binary blob or a big binary data stream, and we need to decide what is this and what does this do. So when we view reverse engineering through this lens, I think there's two ever-present issues that we need to be able to address. And the first is how we conceptualize binary information. The second is how we use our conceptualization for analysis. And I think there are big flaws with the way we approach both of these issues. And that's sort of what I want to tackle today. So let's look at the first problem, how we conceptualize binary information. Sort of brings us to what I consider to be an RE dichotomy. There's two polar opposite approaches here, and they're basically mutually exclusive, where on the left we have our conventional approach, which is essentially a hex dump of information. It gives us the raw binary information. It's very flexible because this doesn't tell us what the information is. It leaves that analysis up to us. It's also a very exact representation of the data. There's no question that what I'm seeing is what the data really is. Unfortunately, it's unreasonably complex, and it's very difficult to deal with information this way. So most people tend to go to the alternate approach, something like a disassembly. It tends to be something very rigid, and it's governed by rules and structure, but it has the benefit of being very succinct, and it's very easy for us to comprehend this. So it's not so much that I have a problem with either of these two approaches of conceptualizing binary information. The real problem is that there's a giant chasm between these two, and it's completely empty. There's really no software, no conceptualization approaches that bridge this gap here, and that's one of the issues I want to address. And if we look at the second problem, how we use that conceptualization of binary information for an analysis of binary data, here what we're looking at is essentially the questions of what does this do, or where's the vulnerability, questions reverse engineers are usually interested in. And I know guys who can look at a function graph and instantly tell you what that function is doing without even reading the disassembly, just by the way the nodes are connected. Alternatively, I know guys who can just leaf through hundreds of pages of disassembly and instantly find the vulnerabilities there. And it's a pretty amazing ability, but what I find is these guys usually have a lot of trouble telling you how they came to their conclusions. And I think the reason for that is that in its current state, reverse engineering is very much an art, and I think there's a problem with that because we're far enough along, we've been doing this for long enough, we should have better approaches for this. So I want to fix those problems. I want to bridge the gap in our analysis tools, find some happy medium between hex dumps and our high-level analysis tools like IDA Pro. And I also want to change RE from an art to a science. So those are ambitious goals, so how can we accomplish those things? Well, I think we have the tools available through two things. The first is going to be what I call visual reverse engineering. This is going to address the issue of binary conceptualization, how we understand binary data. The second way we can tackle these problems is through statistical exploration techniques, and this is going to address the issue of how we analyze binary information. So the statistical side of things gets a little dry unless you're really into math, and it's really goes into too much depth that I don't have time to cover today. So we're going to mostly skip over this. I'll show you some of the ways we can use statistics, but I'm not going to go into the algorithms in too much depth. What I really want to focus on is the visual RE side of things, which I think is really the more interesting approach for most people. So let's dive into that and see what I mean by visual reverse engineering. So the idea here is that we can take a computationally difficult task and translate it into a problem that our brains do very well. So in this example, we're going to take the difficult task of understanding binary information and translate that to something we're very good at. In this case, that is understanding visual information. So our visual cortexes are very powerful. We are really good at processing 3D and spatial information. So if we can find a way to translate binary information to visual representations, we can analyze it much faster than normally possible. So in other words, I'm going to find a way to traverse 100,000 pages of binary garbage in a very short amount of time. And we're going to understand exactly what was in there, just as if we had been looking at the hexadecimal itself. The fundamental idea here is that if we fundamentally change the way we process binary information, we can find unexpected ways of making sense of it. So that's really what I'm trying to accomplish. And if you've never spent 30 hours looking at a hex dump, wondering what the heck is this stuff, you might be wondering, why bother? Aren't our current analysis tools powerful enough that they already do what we need? And the answer is they're absolutely not. And there are a lot of reasons for that, but I want to focus on two big ones. So the biggest issue I see is that our best reverse engineering tools are completely dependent on a known structure. So the problem with that is that information is evolving faster than our tools can keep up with it. So every day there's a new instruction set, there's a new data format, a new file format, some new format that we need to be able to support. And our tools have to constantly play catch up in order to be able to analyze this type of information. And it's a losing game. This stuff's just exploding at a rate that we can't keep up with. So being tied to structure in this way is hugely problematic. We need to find a better way of analyzing information that's completely independent of structure if we want to be able to keep up with things. The other issue might be colloquially called Gates's law, named after that guy that we all love. So this essentially says that software is getting slower more rapidly than hardware becomes faster. It's basically the counter to Moore's law. And what this means from a reverse engineering perspective is that the amount of information we need to analyze is growing exponentially. So if processor power is doubling every 18 months, the number of instructions that processor is actually executing is growing at an even faster rate. So from a reverse engineering perspective, that means we have a lot more information to analyze. And we just can't keep up because our tools aren't becoming exponentially more powerful. There aren't a whole lot of new reverse engineers able to tackle these problems, and we're not getting any better at collaborating on reverse engineering problems, which means this is another losing game. We're never going to be able to keep up with things at the pace we're currently going. So I think this is a really big problem in reverse engineering, and if you haven't run across this already, I think you're going to see this more and more in the future. So this needs to be addressed, and I was sort of shocked to find when I started investigating this that there are only really two people who have done any sort of real research into this field. Two guys named Greg Conti and Aldo Cortese, both brilliant guys, and I want to talk a little bit about some of their work into this field and talk about how we can extend what they've done. So Conti I'll talk about first. He's a smart guy, teaches at the United States Military Academy, and at 2010 at Black Hat, he gave a presentation that still to date is the best Black Hat presentation I've ever seen. So I'll talk a little bit about what he talked about there. And Cortese is the other guy I want to look at. He runs a small software company called Nullcube, and he runs a blog called Corte.c. So if you're interested in malware or reverse engineering, it's a great blog to read, and I'll introduce some of his ideas as well. But let's look at Conti first. Conti posited that even in unstructured data, there is some type of structure. And barring any other information about what type of information we're looking at, we can assume that sequential bytes have some kind of implicit relationship. So Conti's only dilemma is how do we conceptualize and understand that relationship if we have no idea what it is? And so here's where Conti's genius comes into play. He came up with a very simple approach for visualizing the relationship between sequential bytes and data. He said what we're going to do is take sequential bytes in a string of information and translate those to XY coordinates. So in this case, if we have a string like DerbyCon, we're just going to take all the sequential bytes in the string and translate those to XY. So D is ASCII hex 64, E is ASCII hex 65, that becomes 64, 65 in XY coordinates. And we're just going to plot those in a Cartesian system here. And when we do that, what we start to see is remarkable patterns for any type of information we're trying to look at. So here's what Conti found when you look at ASCII information. So even though this algorithm had no concept of what type of structure was within ASCII information, we see clear structure and patterns in the visual representation through this algorithm. So what we're actually seeing here are these different artifacts that are each caused by some type of structure, some type of relationship in the ASCII data. So this is caused by lowercase letters followed by lowercase letters. This is uppercase followed by uppercase, uppercase by lowercase, lowercase by uppercase. And these various lines are caused by /r/n spaces. So all of those implicit relationships, the way that data is intrinsically laid out within ASCII data results in structure that we can see here. And he found that regardless of what type of information you're looking at, there's clear structure. So here he's looking at image data, here he's looking at audio data. And the benefit here is I can almost instantly learn to recognize these images for what they are, whereas trying to analyze that information at a hexadecimal level would take a tremendous amount of time. So I think this was a big step forward in improving the way that we conceptualize binary information. But that's really just the tip of the iceberg, and that's where we started our investigation. But before I get into that, let me look at some of the stuff a guy named Cortese did. So unfortunately, I had to chop most of Cortese's slides for the sake of brevity, but he found a way to use a fractal called the Hilbert curve to improve the way we conceptualize binary information. Essentially, what he found is that if we map data to this curve first before presenting it to the user, we have this important aspect that we preserve locality, which assists our brains in interpreting information. So without going into the details of that, here he's mapped data to a Hilbert curve, and here he's laid things out in a more intuitive fashion, line by line. But what this shows us is that we can get more detailed information from the Hilbert translation when we look at it this way. So tiny little artifacts like this little red block here indicate unique features inside of this data set that I can't see without mapping it to the Hilbert curve first. So we make extensive use of this Hilbert curve in our software. And I'll leave it up to you to visit Cortese's site if you're interested in more information about how that can be used. But that basically brings us to software we've been developing. I thought these guys had some really great ideas. Canto and Cortese are two brilliant people, but I felt like they didn't bring their ideas to their fullest potential. They didn't pursue things as far as they really could have gone. So I wanted to take it further than they ever did. So Canto has some software called binviz that you can get at his website. And I tried to use that for binary analysis, but it just wasn't robust enough. It couldn't give me enough information to do any sort of meaningful analysis on binary data. So I wanted to go further than that. Similarly, Cortese had these Python scripts that could generate these images, but reverse engineering is a very interactive process. So I needed interactive software. I didn't want to be staring at some static image and trying to get information from that. So that's sort of where we pick things up. And our big goal when we were designing the software was to find a way to understand binary information that was independent of format. And that's the key. That's what sets us apart from any other tools that are out there right now. We can analyze unknown code, format deviations, proprietary structure, anything at all, as easily as we can analyze well-structured data. And that gives us a powerful advantage over a lot of the traditional reverse engineering tools. It gives us the ability to analyze structure a priori without any prior knowledge about what that structure really is. So the software we've developed is called Canto Dust, and I am a ridiculously nerdy person. I actually have a top 10 list of my favorite mathematicians, and Georg Cantor is second on my list. I wanted to name some software after him, so that's where software gets its name. For some reason, people always think I say Cancer Dust. It's a weird name, but it's not that weird. So this is not Cancer Dust, it's Canto Dust. And really, I'm going to be demonstrating the software today, but what I'm really trying to do is illustrate concepts. It doesn't need to be the software. Anybody could implement this stuff, and I'd like to see more of this in the future. It's just that right now, this is the only thing available to illustrate these concepts. So let's actually dive into things with a demonstration of our software. I want to look at, give you a quick overview of essentially our interface first, so that you can sort of follow what I'm doing as I'm using this. It takes a little while to load up all this pre-computed data that we have. So what we've done is launch this up. It already loaded Notepad++ for us to explore. And what we have on the left here are two navigation panes. This gives us a very intuitive layout of the binary information within this file. And what I can do is select a small window within this information on this left pane, and then I can narrow that window on the right pane here. And this window here gives me the visual representation of the binary data within this window. And over here are all the different translation techniques, all the different ways that we can translate this binary information into visual information. So we have some very simple, straightforward ones, like I've got a hex editor in here. Even though I'm trying to replace hex editors, there's really no alternative in some situations. Or we have some common statistical analysis methods, like looking at histogram view of byte distributions. But I don't really want to look at those today. Those aren't really very interesting or new. What I want to look at is some of the new methods we have to analyze information. So first, let's examine some of Canto's ideas. So Canto had this idea of this digraph system. And I'm going to call this a two-tuple system because I've extended this to other dimensions. But let's look at x86 code in Canto's digraph. So this is what x86 looks like in this digraph view. And the striking features you see here are essentially these horizontal and vertical lines. So the most amazing aspect of Canto's research that I haven't mentioned yet is that similar classes of data have similar patterns associated with them. So any type of machine code I look at is going to have similar features as to what I'm looking at now, but they're all going to be visually distinct. So I can load in something very similar to x86, like x64, and it has a similar but clearly distinct pattern. So the benefit here is that, well, I can look at this hex and I can actually tell you that this is x64, but the only reason I'm able to do that is because I've been looking at information like this for 3 years. It takes a tremendous amount of time to learn to recognize information at this level. But it takes only 3 minutes to learn to recognize these pictures. And the benefit here is I can look at anything, even stuff I'm not familiar with. Like I've never worked in PowerPC, but I can instantly recognize that I'm looking at some type of machine code based on these visual patterns, even though I would never have any idea I was looking at machine code based on the hex dump. So that's the benefit of visualizing information in this way. It gives us a much faster way of understanding what type of binary data we're looking at. So I thought Conti had a neat idea with this two-tuple system, but what I found is you can't always get the information you want from a two-tuple system. Sometimes you need to go to higher dimensions, and the more dimensions you add, the better your analysis can be. So what I found is that when we extend this to 3 dimensions, we can actually get much more in-depth information than we could ever get with Conti's original idea. So we can pull up our 3-dimensional visualization of notepad.exe is what I dropped into here. And the idea here is same concept, that I'm going to scrub through the data and watch the way the visual patterns change. And through these pattern changes, I can understand exactly what I'm looking at within this file without ever having to go to a hexadecimal level, without ever trying to have to understand binary information at something this low level. So it gives me a much faster, more powerful way of analyzing and understanding information. So just like we have all these different visualization techniques here, what you'll find is that some techniques are good for some types of analysis, others are good for other types of analysis. And similarly, some translation mechanisms within a technique tend to be good for finding certain types of data. So right now we're translating binary fragments to 3-dimensional information, but we can actually change the way we translate that. So we can translate it to 2-dimensional information first, and then layer these 2-dimensional images on top of one another to give us a different representation of the binary information. We can also change the coordinate system. So what you'll find is some types of information are more easily analyzed in a spherical coordinate system. Some types are more easily analyzed in a cylindrical coordinate system. And you learn to just get a feel for what the right approach is for the type of information you're trying to find. And I don't want to get too sidetracked because I don't have a ton of time here, but if you ever get really bored, sometimes looking at hexadecimal for hours and hours on end can be mind-numbing. So there are a lot of Easter eggs that I've put in here just whenever I got really tired of working with this stuff. Particle effects are fun to play around with. So whenever you're done being lazy, you can just go back to work. So there's really no reason for that, but it's some fun stuff we can do. So let's start off with the extensions for Conti's original ideas that we've investigated. Let's look at some of the ideas we can investigate for some of Cortese's work. So Cortese had this idea of viewing information through Hilbert transformations, and he also looked at visualizing entropy. So what can entropy tell us? Well, if you're not familiar with entropy, it is simply a measure of randomness, and areas of high entropy or high randomness tend to be areas that are very useful for reverse engineers. So high entropy areas could be something like encryption keys. It can also indicate packing. You can also look at entropy differentials in order to find key features of information. So for example, x86 has a certain amount of entropy typically associated with it, but if you try to obfuscate your x86 code by adding all sorts of weird jumps or odd constructs, that's going to implicitly change the entropy associated with your code. So by visualizing the entropy, we can find changes in minute details in data that we couldn't normally see from a raw hexadecimal view. So some of the more obvious examples where entropy are useful, one would be malware analysis. So one thing malware loves to do is it loves to pack itself, which thwarts simple static analysis techniques. So I dropped a piece of malware in here, and we can visualize the entropy within this piece of malware, where pink is very high entropy and blue is much lower entropy. So this entire region of this malware image is all packed stuff, which means I can't really work at it right now. But the malware entry point is going to be in this lower entropy region, and this is how it's going to decompress. Basically, in this low entropy region, it's going to decompress the packed malware. So as a reverse engineer, this gives me valuable information about where I want to start with my analysis. I'm going to begin my analysis in the low entropy region to understand how it's going to unpack the high entropy region. So that's an example of how we can get some key features and a better idea of what we're looking at through these metric visualization techniques. Another one I want to look at is a commercial software, one of my favorite hex editors, and I don't want to get them in trouble, so I'm not going to name any names, but you might be able to recognize it. So if we look at the entropy within this commercial piece of software, we see a very high entropy region here. So I was a little bit curious about what that was. So we can zoom in on this high entropy region and try to find out exactly what this is. If we pull up our hex view here, and mouse over this, what we'll see at the very beginning of this high entropy region is a PNG header. So PNG is a type of compressed image format, which means it's just a compressed image. That's what causes the high entropy there. So that's not too interesting if you're a reverse engineer. On the other hand, if you're a forensics analyst, you might be interested in images or something like that, memory dumps. So that could be useful for you, but as a reverse engineer, I'm just going to skip over this part. I was interested in this little detail down here, and if we zoom in on that in a hex view, it doesn't look like much, but I investigated it more in IDA Pro, and that turns out to be the key checker algorithm in this piece of software. They've tried to obfuscate it and pack it to prevent you from stealing your software, but in doing so, they've altered the entropy for this region of information, which gives us a clear indication that that's a key feature that we want to investigate more. So we have dozens of different metrics that we can run on this binary information, not just entropy, and we can get all sorts of interesting details like that from these various metrics. So that's sort of the idea that Cortese investigated. Let's look at an actual practical example of dissecting a file using these techniques. I'm going to look at notepad.exe here, and obviously you can drop this file into a tool like IDA Pro, and IDA will tell you exactly what the different pieces of notepad.exe are. But it's only able to do that because it knows exactly how to parse a PE file. It's basically governed by a set of rigid rules, and with those rules it can break apart this information. But we don't want to be tied to those rules. We want some other way to analyze information. So that's where this software comes in. Without ever knowing anything about how a PE file is laid out, we're able to dissect the software through these visualization techniques. So what I'm going to do is select a small window at the beginning of notepad.exe and begin analyzing these visualizations in order to understand exactly what information is in this file. So this is a 3D visualization for x64 data. You can tell by these heavy bands right here and going across there, and a vertical one here, tell me that this is x64. And as I gradually scrub through this file, I'm going to see new artifacts. So right here we saw these this purple stuff up here in the middle here, and what this is essentially a set of small cubes inside of our larger cube. That's the 3D pattern for English ASCII information. And if you look really closely, you can see that it's projected onto each face of this cube. So here's a little projection of those cubes. Here's a projection here. That actually tells us that these are null terminated strings. What does that mean from a reverse engineering perspective? Not a whole lot, but it's just an example of how we can get very detailed, very accurate information about what type of data we're looking at through these visual representations. So if we continue scrubbing through here, what we're going to see next is artifacts associated with a bitmap image. Specifically, we're looking at an RGB image here, and if we see if I can pull this up. So what you see here is a long streak moving through the middle of the cube, and then that streak's projected onto 3 faces of the cube. So the fact that it's projected onto these faces can tell you that there's an unused alpha channel in this image information. But again, as a reverse engineer, that's not something I'm overly concerned with. If we continue, we'll see this overcome with static, which suggests we're going into a compressed region in this file. And if we go to the end, we'll see more artifacts associated with a different type of image aid. And you can actually see the notepad icons appearing in our byte plot view of things. So just an example of how we can quickly dissect information. If we want, we can actually switch to other visualization techniques to get more information out of this. So for example, here is where I see this very clear, distinct bitmap data pattern, and using our metric map visualization in a linear layout and shading by bytes, we can actually pull out this image, even though our software knows absolutely nothing about how bitmaps are laid out. Just by changing the way that we translate that information to visual abstractions, we can actually pull out what that image is. So in this case, it's the genuine Windows logo, which I don't even think appears in notepad.exe, but they use 10% of the file for that. So that's Microsoft's way. So those are sort of the ideas that other people have come up with. I mean, we've extended those to make those more interactive and more useful for real analysis, but now I want to get into the ideas that we've developed ourselves. So one of the more powerful approaches we've found is binary classification. So what I wanted to accomplish here is essentially what we saw earlier, just a second ago, is going through this file and identifying the regions based on these patterns. But I wanted to automate that process through a statistical analysis, and that's what we've managed to do through these classification algorithms. What we do is I take some binary data that represents a sample of something I'm looking for. So for example, if I want to find x86, I can compile x86 out of some other file and supply that as a template to my software. So the key here is I'm just saying this is what x86 looks like. I'm not completely defining x86. x86. I'm not giving it a grammar. I'm not telling it how to parse x86. I'm just giving it a sample of x86 code. And I'm going to give it a whole bunch of these different templates. And from these templates, our software builds what are called n-gram models. And we do a statistical algorithm called naive Bayes classification algorithm in order to classify regions of the file as most closely matching various templates. So now I can feed any arbitrary file into our software, and it will run it against these templates in order to identify the different regions. So here it's saying, well, this region most closely matches, from a statistical pattern perspective, this most closely matches your x86 template. This most closely matches your compressed template. This looks like ASCII here. So it's a neat automated way to do file carving, but it has uses far beyond that. So one of the things we'll see coming up is using this to identify custom and proprietary formats. We'll actually look at finding custom compressed modules inside of a firmware image through this type of statistical matching technique. This also lets us examine unique instruction sets. So one of the things malware loves to do is invent their own instruction set and then run it inside of a custom virtual machine. And if you're used to dealing with well-structured information, you don't really appreciate how hard it can be to differentiate between code and data, but in some of this malware that can be incredibly difficult. But with these statistical matching techniques, we can automate that process. As long as I can find a small snippet of instructions from this piece of malware or whatever I'm looking for, I can supply it as a template and then find that throughout the rest of the file based on the patterns present in that data. And we're not quite here yet, but where I eventually want to get to with this is being able to identify data and code features. So say I'm looking at a file that's entirely x86, but I want to find cryptographic algorithms in that file. Well, cryptographic algorithms are going to have a different distribution, different patterns of bytes and instructions than normal x86. So I can feed in a cryptographic x86 algorithm and say, find more stuff that looks like this. It will be able to parse that. It'll be able to parse through a file and look for things that statistically match that. It'll be able to say, well, here are the other cryptographic algorithms within this file. So it's a really powerful idea, I think, that's going to save us a lot of time in reverse engineering. One of the other things we've looked at is what I call probabilistic parsing. So conventional parsing, conventional disassembly falls into two categories. Usually recursive descent, which is what IDA is. Recursive descent disassembly starts at a beginning point and it tries to follow the path of execution when it's doing the disassembly. Linear sweep disassembly is something like objdump. It starts at the beginning of a file and just moves forward linearly. It doesn't care about where execution would actually go to. Both these have their pros and cons, but well, I like the information you can get from these. You can get a lot of important information about how functions relate to each other. The problem is I didn't want our software to be dependent on any specific type of structure. I don't want to be tied to x86 or ARM like that. So I don't want to give it knowledge of how to parse these things. I still want the ability to gain the benefits of parsing. So what we came up with is what's called probabilistic parsing. We're actually able to identify call graphs inside of an arbitrary binary file through statistical patterns rather than grammar definitions. So what we're looking at here is essentially a call graph for a file that I gave that was parsed using statistics rather than disassembly directly. This gives us a really powerful ability to analyze information. So I can run the exact same algorithm on x86 or on ARM or on some instruction set that comes out tomorrow that nobody's ever seen before, and we'll still be able to generate these function graphs. And I'll show you coming up how that can be incredibly useful. Because what I want to look at next is an actual case study, how we can use these techniques we've talked about for a real-world example of simplifying our lives as reverse engineers. And what I'm going to look at specifically is a topic brought up by a group called the Invisible Things Lab. So if you're not familiar with these guys, it's just a small group of people. I think it's 3 guys and a girl who are really, really brilliant. They're coming out with some of the best exploits I've ever seen. And unfortunately, I can't pronounce their names, but they gave a presentation at Black Hat a few years ago that they called as Hacking Intel BIOS. And it was a really neat idea, and that's what I want to look at in more depth using these analysis techniques. So their goal in this paper was to bypass EFI signing protection. And just a little bit of background, EFI is basically a BIOS replacement. It's supposed to be more structured, more extensible, and more secure. And one of the things you can do with EFI is you can one of the ways it's more secure is it can be configured so that it requires signed images if you want to reflash your BIOS or EFI. That way you can't get unexpected code installed in the firmware of your system because it has to be signed. So that's supposed to make it more secure, but these guys had invisible things who wanted to get around that. So what they did is they started investigating EFI images, and they found that the image itself is not signed. The image is only an envelope with a CRC checksum, but inside of that envelope are signed modules. So they found signed module after signed module after signed module, and then they came across an unsigned module, which was a perfect attack vector. We can flash this unsigned module without having to sign it, which gives us a way into the system. So Why would you do that? Why would you require signing on these things to improve security and then give the opportunity for an unsigned module? Well, the reason for this is the unsigned module is the boot splash logo. So when you first press the power button on your PC, the image that comes up is the splash screen. That's an unsigned module in this EFI system. And the reason they leave that unsigned is because they want OEMs to be able to add their own splash screen to the system without having to go through the trouble of signing things. So that's an interesting possibility for an exploit here, and they found a way to leverage this to their advantage. Their goal was to get unsigned code execution. They want their own code running instead of the BIOS so they can get early control of the system, but they can't update the code. The code has to be signed, but they can only update the bitmap. But what they did is they found a vulnerability in the bitmap parser for the splash screen. So most EFI code comes from this EFI template code provided by Intel, and then IBVs or independent BIOS vendors use that code for their EFI development. So finding a vulnerability in this template code means that you're finding a vulnerability in almost every EFI system out there. So they found that they could flash the bitmap with an invalid image by manipulating the width and height to get an overflow when this image is parsed. And through that overflow, they can get code execution early on in the BIOS boot process. So that's a pretty powerful ability. And I wanted to look at that in more depth. Well, one observation we need to make before we go forward is that no one is really EFI, and Invisible Thing sort of glosses over this fact. They make it look like this is a fairly straightforward hack. But it's not at all, because BIOS vendors have a lot of legacy code, and they're gradually moving towards EFI, but they're not really willing to give up their legacy code yet. So what you find are systems that are 25% EFI and 75% legacy BIOS, or something like that. What that means from our perspective is that we can still use this vulnerability, but we're dealing with much less structure than EFI would provide, because we're dealing with more BIOS, and BIOS is very unstructured. Less structure means more headache, but it also gives us a perfect opportunity to use this tool we've developed, which is very resilient to unstructured information. So ITL covered the actual exploitation process. I want to figure out everything else. The first step is going to be to choose a victim laptop. I just chose this junk laptop I had lying around that's held together by duct tape and staples and scrap metal, basically. So I didn't care if I break this thing. It was the perfect system to test on. You go to this laptop's website, download the executable for a BIOS update, and what you get is essentially this. You have to do some quick RE. They've tried to hide the flags from you so that you can't spit out the actual EFI image, but what you see is all they did is they added one to each ASCII character in the flags. So if you just subtract one from all these strings, you can figure out what the flags for this EXE are, and there's one called write ROM file. So when you give it the write ROM file flag, it'll spit out the EFI image that we want to analyze. So let's go ahead and pull this image up in IDA. And we don't get a lot of information here because IDA can't deal with unstructured data like this. And you had to know a little bit about how execution begins when a processor is first powered on. But if you know that, then you can figure out where the entry point to this information is. And it's essentially right around here. Is where execution begins when your computer first starts up. And what we want to do is go trace execution down to the bottom here. They've got this function loop down here, which is essentially executing a list of functions that they provide here. And most of these have to do with hardware initialization. We're not too concerned about most of these, but the very last one I am interested in. If we go to that, see what they're doing is they are loading in this module. This happens to be a module that's undergone custom compression. It has no standard headers. It has no type of format that anybody's ever seen before, which makes this very difficult to analyze. But what they're going to do is decompress this module with this decompression routine. So I looked at this module a little bit, but it wasn't the module we're interested in. We're trying to find the module that has to do with the splash screen. But if you look through this file, you won't see anything that looks at all like a splash screen. It turns out it's in another module somewhere. We need to find where that other module is. So odds are they're going to be using the same decompression routine. So one way to try to find the other modules is look at xrefs, this decompression routine. There's only one other place where this is called. Unfortunately, this function is not called anywhere else in this binary. It turns out that this function is only called from that compressed module. So in order to find out what parameters are being passed to this function, in order to find the other modules, we need to reverse engineer that first module that we found, and we could be chasing our tails for a very long time trying to go down that path to find the splash screen module. But this is where statistical analysis can help us in the reverse engineering process. So what I'm going to do is connect to the IDA database, pull this into our software here, and fire this up. And what I did is I went to the module that we had already found, and I basically highlighted all this, cropped it out, and supplied it as a template to our software. So now I can run our statistical matching algorithm against this database and pull out regions of this file that most closely match that compressed module. So it's something we really can't do with traditional tools because this module has no kind of standard format for us to look for. But through a statistical analysis, we can find things that look like this module, and it does a pretty decent job where found the x86 code that we were already looking at is over here. Here's the original module that we gave as a template. Found a compressed region here, but it couldn't identify what this exactly was. It found some ASCII here. Most importantly, it found this region here is a region that statistically matches the module that we gave it. So this is all the other modules in this, this file that we can now pull out and analyze in more depth. So I need to find out exactly where those began. So if we try to do that, turns out they start right up here. So now that I know where the modules begin, I can crop these out, and I use a plugin for IDA. If you're familiar with IDA, you should know about a guy named Chris Eagle who wrote a plugin called x86mu, which allows you to emulate x86 code. So using this, you can actually emulate that decompression routine and give it the modules that you found in order to decompress these modules without ever having to understand the algorithm. So that's a really neat ability. And what you end up with are these 20 or 30 some modules. The problem is they're also proprietary structure, which means if you run something like file on them to try to figure out what they are, they're all basically data. We get 2 false positives here, which are pretty common, and with the file command. So here's normally where you'd have to start looking at these things in a hex editor in order to figure out what these are. But here's another chance for us to utilize the binary visualization powers of the software in order to figure out what we're looking for. So what I did is I catted all those modules together, and I'm going to drop those into here and use Conti's technique of a 2-tuple system in order to visualize the information within these files. What I'm trying to find is something that looks like a bitmap image. I'm going to scrub through this and look for a pattern that looks like bitmap data, and that will be theoretically the splash screen that we're looking for in order to implement this exploit. So right here is a pattern I recognize. It's a little bit faint, but I think we can pull this, try to make this a little bit stronger. This is a pattern I've recognized as associated with 4 bits per pixels bitmap image. And if we try to zoom in on this region and change the way we're rendering this information, we can actually see that this is indeed the splash screen that we're looking for. So anyway, so that's Dell, and that's essentially the system we're working with. So that's the splash screen that would come up. So if we mouse over here, we can see where that is in our catted image. We can find out that this was part of this mod E. If we pull that up in a hex editor, what you'll eventually see is that this is actually following the bitmap format, but they stripped off the bitmap header. The bitmap header is the characters BM at the beginning of the file. And all they did is delete those 2 characters, which breaks all of our normal analysis tools. It means we normally can't recognize this information for what it is. But if you open that up in a hex editor and add those 2 characters back in, you can then drop it into something like O&O, which understands bitmap information very well. And O&O can show you exactly where the width and height fields in a bitmap are, so that you can modify those in order to implement this exploit without having to do any serious RE. So at this point, we have everything we should need in order to do this exploit. So it should just be a matter of repackaging this modified splash screen, shoving it back into the envelope, and trying to flash the computer. Unfortunately, it doesn't work if you try to do that. It's not a signing issue. The modules are signed and the bitmap's not, so it's okay that the bitmap's not signed. It turns out it's an issue with the envelope checksum. So in order to get this to flash, we need to fix the checksum in the envelope. So this gives us another perfect example of where we can use some of these analysis techniques we found. So what we need to do is find out what type of checksum they're using and where it's stored within this binary EFI image. So what I'm going to do is pull up that very first module we found. The raw EFI image doesn't do much other than initialize hardware, so it's pretty reasonable to expect that the first module that is extracted and executed is going to have something important and interesting. Unfortunately, when you load that module into IDA, you get nothing, because IDA doesn't recognize this format. It doesn't know where to begin. It's waiting for you to tell it what to do. So that's a problem for us. But again, that's where this type of software comes into play. So we're going to import our IDA database again, and what I want to show is the statistical parsing method I discussed earlier. What this lets us do is Does this show up? Yeah, it shows up more or less. What this lets us do is find relationships between functions via statistical patterns rather than trying to parse things like IDA would try to do. So I can select any arbitrary window within this file and view the functional connections within this region. Now, I don't know where the checksum routines are, so I need to view this entire file. And since that's going to be a lot of data, I'm going to crank up the number of nodes we're looking at. And we end up with this ridiculously awful, horrible mess. It looks like a spaghetti monster to me. But what this is showing us are essentially a call graph for this entire file. And when I don't know where else to begin, I usually like to look at who's called the most. So I can shape this by who gets called the most. And this is telling me that, statistically speaking, there's almost certainly a function here that is called more than any other in this file. And if we go to that position in the IDA database, we'll see that, indeed, there is a function there. And I'm not going to walk through the reverse engineering of this function. But if you do that, you'll see it's really nothing interesting. It's just a dispatch function. It's a way to wrap other information. So I'm interested in the next most called function, which is going to be, statistically speaking, most likely right here. So if we look at that guy, again, it is a function. We pulled it out correctly, and we see what it calls. What you're going to see is it accessing some interesting characters. It accesses % plus minus 0, 9, L, H, C, S, X, D. You might recognize these as placeholder tokens from a printf. So D is going to be decimal, S is string, X is hex, C is char. So what this is a printf function. But if you look at it in a little bit more depth, you'll see it's not just printf. These aren't going, this printf isn't going to the screen. It's actually going to a debug port, which means that this is some kind of debug printf. So if they're printing out diagnostic information, that is definitely something I'm interested in. So I wanted to explore this function just a little bit more. So right now this whole thing's kind of a mess, so we can crop out just this function. And I'm going to change this to a two-dimensional layout because it's a little bit easier to work with things in 2 dimensions when you're dealing with a smaller amount of information. So here's my printf function, and all these are the nodes that call printf. So right now I'm not really interested in which one's called the most. I'm rather interested in who is calling printf the most. So I can change the way I'm shading information and pull out this function here that is, again, statistically most likely to be the one that's calling printf more than any other function in this binary file. So if I make that into a function, I see, just as statistics predicted, this calls printf quite a bit. But it turns out this is just messing with ports. That's really not something I'm interested in. Unfortunately, the rest of these, all these nodes are about the same size, which means all these are calling printf about the same amount. But 2 of these were more interesting than the others. These guys here and these guys here, because these indicate a higher level of complexity than we see with the other nodes. Because not only is this node calling printf, but one of its children, one of its subfunctions is also calling printf. So that's something I wanted to investigate in more depth. So if we look at those guys, we see this one we just looked at is a bootb flash recover. So flash recovery algorithms are pretty interesting, but not really what I'm looking for. So I wanted to look at this other one instead. If we try to pull out that function, I'd already found it since we gave it some starting points. This turns out to be what we're looking for. Validate RBU, that's remote BIOS update CRC. So we statistically found the CRC checksum routines here. We find right here, this is the offset within the image file that we need to replace the CRC at. And if we look inside of some of these, if you don't know much about CRC, there's a lot of different versions of it. They use different magic numbers, different algorithms. So we need to know exactly what version they're using if we want to replicate the correct CRC for our file. So here's the magic number they're using for their CRC checksum. And in here's their actual CRC algorithm. So at this point, we have everything we need to duplicate the correct CRC for our modified image. And again, I can't stress enough that what we did is we pulled out that information through statistical and pattern analysis rather than by parsing things like IDA would try to do, which gives us a great advantage when we're dealing with things that we don't understand the structure for. So at this point, we can repackage our modified splash screen, successfully flash the computer, and I didn't try to get code execution on this thing. I wasn't really interested in that aspect. I just wanted to quickly dissect this. So this whole thing took about 9 hours using the software, and most of that was spent in reverse engineering their compression algorithm because we had to find a way to recompress that splash screen image. I wanted to know how hard it would be without using this software, so I tried it again afterwards, and it took about 37 hours without these statistical and pattern matching algorithms that we've used. So just an example of how this can really help cut down reverse engineering time, make things a lot faster than they would normally be. So that basically concludes what I wanted to show you. And really what I'm trying to get across is we need new ways to understand and analyze binary information because we can't keep up with the way things are changing using our current approaches. And if we don't try to find new ways of doing things, RE is going to stagnate and we're just going to lose the battle. So the point isn't use this software at all. It's just that the software right now is the only way to do some of these techniques. It's really more about thinking differently. Finding new ways to understand and conceptualize information is what we need to do in order to move forward. So if you're interested in this software, there's a demo available at our website. You don't have to memorize the address. If you just search for Canto Dust, that's Canto Dust, not Cancer Dust. If you look for Canto Dust binary visualization, you'll come across our website. And I don't have the demo posted there yet, but I'll try to put that on there. And it'll give you a couple of these visualization techniques to play around with if you're interested in them. And really, we've just gotten started with this software. We're going to be developing this a whole lot more in the future and really add some powerful mathematical and statistical analysis techniques to make this really powerful. And hopefully, we've just scratched the surface. And hopefully, I'll be back here next year with a updated version to show. And I hope everybody will attend to see that. So that's all I've got. Looks like we have about 5 minutes if anybody's got questions.
Just wondered, having built the tool and understanding how you're analyzing the data, what are the countermeasures someone could start using against this now?
Yeah, so that's a really good question. And to be honest, I don't really know of any very good ones yet. So one of the things I didn't have time to show that I might as well pull up now that I have a chance is these translation mechanisms. Translating this information to visual abstractions this way is a really powerful technique. So if I toss in our x64 file, which we saw earlier, it has a pattern like this. Here I took that same file and I inverted all the bits, and it has a very similar pattern. Here I took the same file and I XORed it with a random 8-byte key, and it still maintains its pattern. So the fact is we've got some really powerful techniques for visualizing and understanding this implicit relationship between elements in this data set. And even when you try to damage the actual value of the elements, the relationship remains, which means we can still analyze information this way. So it's a very hard thing to circumvent.
I'm curious. I first assume you process encrypted data through your tool, whether it be streamed or block data, and you perform statistical analysis to see, the correlation of different algorithms, and if you can reverse any of that data.
So far, we haven't really looked at that side of things. We've been looking at mostly analysis of static images is what we've been focused on. As we move forward, we're going to be looking at adding additional layers, so decrypting things, looking at patterns and that type of information. So hopefully next year I'll have a better answer for you.
Notice you can also pull from IDA's database. Thinking through signals analysis, could you see potential of streaming network data into this?
Yeah, so that's one of the next big things on our list is we want to be able to plug this into streaming information. We also want to be able to plug this into processes' address spaces, so I can visualize the entropy as malware unpacks itself, or I can visualize anomalies in your network data streams. We're not there yet because mostly what I do is firmware reverse engineering, and I've designed this to help me with what I do, but we'll be moving there in the near future.
Your call graphs were shown. Those are generated from a grammar-free statistical parsing of the file?
Correct.
Wow. Okay. Can you briefly explain any of the statistical metrics behind that? I'm having trouble wrapping my mind around.
It's complicated.
Okay.
But at a basic level, what we're doing is we have enough people who are very familiar with the way different instructions are constructed, and they all have similar patterns between them, where particularly function calls are usually specified as a relative offset from the current location. It's hard to specify them as anything but that. So we're able to essentially treat every offset as a relative offset to another location, and then we use statistical filters to filter out the noise from that and find what is most likely actual jump and call instructions in order to identify function boundaries. All right, well, more.
A graphics library is
So I've written this in C#, and I'm using X and A for the visualization techniques, which I would not recommend to anybody. It was a horrible choice to go with, but that's what I'm stuck with now because I'm too deep to go back.
It actually performed really well.
It does okay, but it's brutal to work with. All right, well, thank you everybody for showing up, especially this early on a Saturday.